right. Okay, there we go. All right. Finally ready. So we'll get started. So yeah, hopefully you guys had a decent break and got some rest. But if not, you're almost done with this semester, so that's good. But today we're gonna kind of combine theory and modeling. So we're just gonna basically briefly go over the theory because we missed a week. But that'll be okay. I want to focus more on the Simulink stuff anyways, so that'll be fine. But today we're gonna do the modeling for the last lab. I know my slides here. This is wrong. It's experiment 5 and it's week 14. So the slides, they're on Canvas if you want to check that out. And then also the SOQs, they're available too now. So you can either access the SOQs from your email or you can get them on your portal. So check that out. And then, hold on, I'm going to pin my camera. Okay. Yeah, so make sure that you guys do the SOQs because the department, they want to see that there's a lot of responses for that. So make sure you do that by December 11th, I think is the cutoff date. So again, check your email or go on the student portal and then you should be able to access the SOQ. Okay, so I have a kind of a little weird setup today because I need to do the modeling on my laptop today because and you might notice this too. If you open up MATLAB right now on your computer, it might say that you need to renew your license. So you can do that on MATLAB. I'll show you how if you guys didn't already update that. But when I did that on my computer, it messed up some of my installation files. That shouldn't be a problem if you're doing it on, a Mac or Windows. Nothing should go wrong. But anyways, I have to do it on my laptop today. Okay, so we'll kind of go over what we're going to be doing today. So we're going to be doing the basically car suspension. So if you look at the handout that we have here, this is basically what we're going to do. So we have a car that we're going to model for the suspension for our front tires and then the rear tires. So basically this car is going to be, driving along this road here. And because of the surface roughness of the road, really this kind of profile, the height profile here is varying sinusoidally. So we need to model that with the suspension of the car. And basically we're going to look at the bounce for this car, the bounce amplitude specifically. So how much it's going up and down, and then how much the car is rotating for the pitch here about the center of gravity for the car. And basically we're going to start off with some given values here for the for the mass, of course, and then we have the moment of inertia about the center of gravity. And then we're starting out with some stiffness values that we have here. Let me make this bigger. So we're going to start with some stiffness values. So we have 30,000 newtons per meter. That's going to be given to us for the front tires and the suspension, and then the rear tires and the suspension kind of combined. And then we're also going to be given the damping ratio or coefficient that we have for the front tires again, and then for the back tires. And that's going to start out at 3,000 newton seconds per meter. And then the last thing that we're given is our front length here. So it's the length from our front tires to the center of gravity. And then the other length that we have is the rear tires to the center of gravity. Okay, so that's the given. So again, what we want to do is basically build an equation of motion. And then we're going to model that in Simulink. And then we're going to, plug in all of these values here. And we're going to look at how much the car is going up and down, so the bounce, and how much it's pitching as we drive along this varying height profile for the road. And in the end, what we have to do is modify our stiffness, and it should also say, well, here it only says to modify the damping coefficient, but we are also going to modify the stiffness coefficient until we can get a bounce amplitude and a pitch angle that's less than 2.5 millimeters and 10 to the negative 3 radians, and at steady state. So basically this part here, this is what you're going to be working on by yourself. Shouldn't be too bad, you're just going to be changing the stiffness ratio or the stiffness coefficient and the damping coefficient. So we're going to be doing the modeling today in class, but as for the theory, we're not going to derive the equation of motion. It's similar to what we did last class for the gantry crane. So basically, you would have to use the Lagrange method, but we're going to skip that part because again, I want to focus more on the Simulink portion for this, which will be on your final later on, which we'll talk about next week. But for your final, basically, I'll give you, well, at least I'm thinking, I'll give you an equation of motion, and then you're going to model that inside of Simulink by yourself. So again, we'll talk about the final next week, but the main focus for this class is Simulink. So any questions before we start modeling? And I'll talk a little bit about the theory a bit more, but again, we're not going to derive the actual equations. I'll just give them to you. Okay, no questions? Oh yeah, one more thing too. The Gantry crane memo that's due today, so hopefully all of you remembered that. So sorry I didn't get your third memos graded yet. I'm sure a lot of you were waiting on that. I didn't get any rest too over the break, unfortunately. I was busy with making this lecture, and then my other class, I have to grade a project. So I'm going to get those memos graded as soon as I can, though, but good news, at least. So far, all of the memos for this class, at least as a whole, they've been really good. So you guys are doing good so far in the class. I know we only have 2 graded, but we only have 5 memos in total. So just keep doing what you're doing, and you guys should be good. Also on Canvas, I know before, if you looked at your grades, it would show like a weird grade, like 300% or something. So I fixed that. Canvas is a little weird with how it displays grades, so I fixed that. So you can look at your actual grade now. I mean, you of course could have calculated it too, but you can check that out. Okay, so let's open up MATLAB. Actually, what I'll first do is show you some of my slides here. So because I'm using my laptop, I can't show the slides like I typically do. So basically, I'll go over some of the first slides that we have here, and then we'll just start modeling. So I already talked about a lot of this, but first thing we have is road roughness. That's going to cause a sinusoidal system response for the car. So again, we're going to have bounce, so that's when our car is going up and down, and then we're going to have pitch when when the car is kind of tilting. And we're going to neglect roll here because it's going to be negligible. So we're not, rolling side to side. Okay, so for this lab, we're going to assume a few things that'll be, some given parameters. So the amplitude of the height profile for the road is going to be 10 millimeters. So if we look at our handout, the amplitude here is going to be 10 millimeters. And then the wavelength is 5 meters. So from this peak to this peak, and this peak to this peak is 5 meters. Okay, so those are the givens, at least a few of them. And then again, we're going to skip this part for the derivation, but we're going to be given an equation of motion. It's going to be another coupled equation of motion. So we have our linear portion, and then we have our rotational portion, which is the tilt. So I might not have you do this part yet. For the lab, I'll give you a deliverables handout again, of course. So I might just have you just focus on adjusting the stiffness and the damping, so you can get a bounce amplitude and a pitch angle that's less than 2.5 millimeters and 10 to the negative 3 radians. Okay, so we're going to put all of this stuff in a MATLAB script. Again, it's all given stuff, besides these two that we're going to change later on. As the only thing I didn't mention before is our car is traveling at 50 kilometers per hour. Okay, so here we are. This is our first equation of motion for the kind of coupled system that we have. So we have our linear portion here for the bounce amplitude. So again, this kind of coordinate axis, or this coordinate that we have, is x, but that's the car bouncing up and down. And then we're also going to have a coordinate of y, and that'll be our tires going up and down on the road. So we have the car itself going up and down, that'll be x, and then we have y, which is basically from the sinusoidal road profile, and that'll be our tires going up and down. So this will make a bit more sense once we start modeling inside of MATLAB. So this is a pretty long equation of motion here, but this is what we have for the linear portion. So again, we're not going to derive it, but you can see we got quite a lot of terms here, so we're going to build it, and basically in the end, we're going to have this. So it's pretty big, but I gotta be honest, I love the way it looks, okay? Because you can kind of easily visualize how it's kind of coupled here. So that's what we're going to do. We have the linear portion on the left here, that kind of equation of motion, and then the rotational or the tilt equation of motion on the right. I forgot to update this. This should of course be connected right here. But yeah. Okay. And it should be connected for to a theta dot, or actually theta. It should be connected right here to theta. Okay, so let's open up MATLAB. I'm gonna change my screen to go on my laptop. Okay, so what I'll do is I'll delete some of this stuff so we can kind of go over it together. So I'm just going to put these side by side for now, just so I can, write all this stuff down, because I didn't memorize it. Okay, so before we really get started though, does anyone have any issues with their MATLAB for your license?
I did a second ago. I just had to reactivate.
Okay.
I still do.
Okay. So if you guys have that issue,
I'm getting
I'll show you what to do.
like a troubleshoot 9 or something like that. It's like, I forgot what, hold on, let me find what it was saying.
Okay. Okay, well, in general, if you guys need to reactivate it, all you have to do is go to help, and then licensing, and then activate software. And then this will pop up, and all you have to do is kind of reactivate it. So you can do it through the internet. So you click next, and then basically you have to sign into MathWorks. So, this is a separate login than what you have for Fullerton.edu, but most likely you're using your school email, and then your password, of course, that depends on what you had for MathWorks before. So type that in, and then all you have to do is, press next, and then you'll be done. So work on that if you didn't do it already, but it's pretty easy to do. So you just got to sign in basically. And while some of you are working on that, I'm just going to type out some of our parameters that we have for the script. Can you guys read the font okay too? Is it big enough?
Yeah, it's good.
Okay. Okay. Okay, so the first thing that we have is the damping coefficient. So that was given to us in the handout. So we're going to start off with 3000, and then later on we're going to, well, you guys are going to modify the damping coefficient and the stiffness coefficient so we can get a better system response. So CF, that's going to stand for the damping coefficient for the front tires and suspension. So we have CF equals 3000, and that'll be damping for the front. Then we have CR, that's the damping for the rear tires and suspension. That's also going to be 3000. And we'll do damping rear. Then we have KF, that's the stiffness for the front tires and suspension. That's going to be 30,000. Then we have KR, that's the stiffness for the rear tires, 30,000. L1, that's our length from the front tires to the center of gravity for the car. So that's 1 meter. So length from front tires to CG. L2, that's going to be 1.5 meters. That's the length from the rear tires to the center of gravity. M, that's our mass, that's 2,000 kilograms. Mass of car. I'm going to put the units, I'm not going to put them just to save time. Amp, that's going to be our amplitude, so that's from the road profile. So remember that was given as what is it, 10 millimeters? So we're going to convert that to meters, so that'll be 0.01 meters. Okay, so amplitude of road. And then we have V, so capital V, that's going to be the velocity of our car. So we're converting that from kilometers per hour to meters per second. So we have 50, that was 50 kilometers per hour. I'm going to do times 1,000 divided by 3,600 to convert that from kilometers per hour to meters per second. So velocity of car. Then we have T, this is going to be our period. So T is going to be 5 divided by V. So we have a 5 here. That's from the wavelength of the road. So remember that was 5 meters, basically going peak to peak. Okay, so we have 5 divided by V. And we're also kind of using that equation there to, we're going to use that to basically get our frequency. So we're going to do our frequency is 2 times pi. And we're converting it to radians per second instead of hertz. So we're doing 2 times pi divided by t, our period. And once we do that, we can get that conversion to radians per second. So that's our frequency. So is our period. Then we have phi, so that's going to be our phase angle. So if you're going to do the geometry there, it basically would be L1 plus L2 times 2 times pi divided by the wavelength, which is 5. Okay, so we can use this phase angle for one of our inputs in Simulink. And then the last thing we have is J, that's the moment of inertia about the center of gravity. And that's given to us as 2,500. So moment of inertia about CG. All right, there we go. I'm going to make all of this a bit neater. I don't know if MATLAB has a better way to align this stuff. If I was doing this in where I usually use MATLAB, I can just use a command to do it. Which is a lot better. Okay. Anyone still working on the MATLAB reactivation?
I am.
Okay. Just forget your password or something for MathWorks.
No, it's a license agreement. It went wrong.
Oh. Okay.
I'm basically like reinstalling it.
You're reinstalling MATLAB?
So what I read to do to fix the problem.
That's weird. Okay, well, if you guys can't get it, of course, this will be, uploaded as soon as I can. Yeah, you should be able to just do the reactivation, but I don't know. Okay, Jared's gonna link a fix he had. What did you do, Jared?
I went on the Fullerton IT website where it has all of the software listed, and when you click under MATLAB, it shows like how to reactivate your license. And I'll have to double check exactly what all the steps were, but it was really easy. You just load the activation part of the software, and you just plug in your Fullerton email and password and all that, and it just runs it like the license verification part before you install it for the first time. But since it's already installed, it just runs the verification again, and then it's done. That's all you have to do.
Yeah, okay. Yeah, that should be all you have to do. If you guys didn't see it before, maybe they show a different way, but all I had to do was go to help, and then not that, go to help, and then licensing, and then activate software. And then a window will pop up, and then you can do it through the internet. At least I did. And then that's when you just type in your account info.
Yeah, I tried doing it the help way initially, but I didn't find where to get like the license part, so I just went and did it another way. So there's two ways to do it, I guess.
Okay. Okay, so hopefully most of you have this done. But yeah, so I'll upload this video, of course, as soon as I can. Once it's done processing on YouTube, which takes, a year and a half. But yeah, so hopefully a lot of you guys have this done though. So we'll run the script and then we'll save it. So I'll call this class suspension script. Okay. All right, so at this point, we're going to open up Simulink. Okay, sorry, let's open up a figure. So, okay, so yeah, there's some other solutions too in the chat, so you guys should look at that. No, it's not sharing my screen correctly now. All right, there we go.
Hey, Patrick.
Mm-hmm.
After I'm running that script, it's giving me an undefined function for phi.
Okay, let's make this bigger. Maybe forgot to define, I don't know, like L1 and L2.
I mean, I have the same thing written as you.
Okay, I'll look at your script maybe after class, but you know it should run.
Oh wait, totally
Yeah.
sorry, my fault. I didn't define L2.
Okay. All right. So Simulink, I'm gonna put this in a new desktop. Okay. So the first thing we're gonna do is define our inputs for the system. So I'm gonna pull up a photo I have for it. Okay, so our inputs, they're going to be Y1 and Y2. So remember that's from our road profile. So Y1, that's going to be for the front tires. And then Y2, that'll be for the rear tires. So we're going to put that in. And remember, it's a sinusoidal height profile that we have on the road. So we're going to use a sine wave. Okay, so once we're in Simulink, we're going to type in sine wave. Okay. And because I'm using my laptop, I'm probably going to be pretty slow here because I have to use my trackpad. Okay, so for our sine wave, we're going to modify some stuff. So we're going to have our amplitude. That's going to be amp. Remember, we defined that in our script. And then we'll do our frequency. That's going to be omega. So we also defined that in our script. That's our frequency in radians per second when we converted it. And that's all we're going to do. So for Y1, we're just going to make the amplitude amp and the frequency omega. Okay, and we'll click apply and then okay. So this is Y1, and then we're going to copy and paste this, and we'll make Y2. So for this, we're going to make the amplitude amp. The frequency is omega, and then for this, we're going to change the phase here since we're at the rear tire. So there's going to be a phase shift here, and we're going to make that phi. And then we'll click apply. All right. So like we did last time, I'm going to use the annotation kind of function that we have. So to make an annotation, we go here on the left and we click on this little box for annotation. And then I'm going to make this size 18 so it's nice and big. And we'll go in the equation editor here. And I'm going to call this Y1. So I'm going to do Y_1. And then I'll give us that little subscript. Okay, so we have Y1, and then we also have Y2. So I'm going to copy and paste that, and I'm going to change this to Y2. Okay, let's move this down a bit. Okay, so again, these are just our inputs for the road profile for the front tires. So that's Y1, and then the rear tires for Y2. All right. So the input for Y1, the amplitude was amp, the frequency was omega, and that's all we changed for Y1. Actually, what I'll do, put this in the chat. So amp equals amp, and then frequency equals omega. And Y2, we have amp equals amp, frequency equals omega, and then phase equals phi. Okay, and what I'll also do is I'm going to rotate these inputs just so I can, kind of format our model a bit better. So we're just going to drag this down for now, and we're not going to worry about it quite yet. So we'll save this. Remember, your model has to be a different name than your script. So I'll do class suspension model. There we go. All right. So we're gonna first start off with our linear portion, or linear equation of motion. So for that, I want to actually show you what it is. I'll go back. Okay, so for our linear equation of motion, we need to basically model this inside of Simulink. Okay, so we're gonna first start out by doing this term, the first term, and then the third term. So we have x dot and x, and then after we kind of put those terms in Simulink, then we're gonna do theta dot and theta, and then we'll do the last four terms down here, which are related to the input from the road. Okay, so that's the kind of attack plan. And then we're gonna sum up all of those terms so we can get the numerator. And then, so that's this summation block here. And then we're going to divide by the mass. And then that'll be our x double dot. All right, and here we go. Okay, so I'm gonna go up on the model now. So hopefully all of you have this. If you don't, of course, y1 and y2, I put that in the chat for what it should be. Make sure you're using a sine wave. Okay, so we're gonna type an integrator. We're gonna have a few integrator blocks. So we have one. I'm gonna copy and paste that. Copy and paste it. Okay, and then we'll connect these. So to the left here, this is going to be x double dot. So I'm going to click on the annotation block again. Make this size 18. Click on the equation editor. And we're going to do a backslash d dot. That stands for double dot. And then in curly braces, we're going to type in x. Okay, so that's x double dot. And then here, this is going to be x dot. So this is our velocity. And then once we integrate that, that'll be our position. So I say position, but that's the amplitude that we have for the car. Okay, so this is what we're going to be looking at as we're done with our model. And then, once you change your damping and your stiffness, you're going to be looking at X. So you can see kind of the result for the amplitude for the car itself. Okay, so we want to minimize that to less than 2.5 millimeters. I think that's what it was. Okay, so there we go. So now we're going to be putting in the terms for x dot and x again for the numerator. So I can't show the slides on my laptop. So if you have the slides on your computer, you can kind of follow along like that. But for the first term for x dot, that's going to be negative CF, so that's the damping for the front tires, minus CR, which is the damping for the rear tires. So for that, we're going to use a gain block. And I'm going to do Command I so I can just flip it. Again, this is just for making the model look a bit nicer. So for the gain block, I'm going to do a negative sign out in front, and then we have CF plus CR. Okay, so again, of course, this term is just negative CF minus CR. Okay, I'll click apply. And I'll make this bigger so you can actually see the terms as well. Okay, so now we have this block, and what we have to do is just hook it up to x dot. Okay, so we have that term, and now we need to get the term for x. So I'm going to copy and paste this gain block. I'm going to modify this. This is going to be a negative out in front, and then we have kf plus kr. So it's similar to our damping coefficient, but instead we're doing this for stiffness. And this is going to connect to x. I'm going to move these down. Okay, so we have our first two terms for our linear equation of motion. which is just x dot and x. Okay, so now we're going to do this for theta dot and theta. So, for now, we don't have anything for theta dot or theta, so we're just going to put in the blocks here. And later on, we're going to actually kind of build theta dot and theta for that equation of motion. And then we'll connect them all. Okay, so we're going to copy and paste our gain block. And for this is going to, later on, it's going to connect to theta dot. So for this term, if you look at the slides, it's negative CF, so the damping for the front tires, times L1 squared. So L1, remember that's the length from the front tires to the center of gravity, minus CR times L2 squared. Okay, I'll click apply and OK. Oh, gosh, I just deleted it. I typed it wrong. Okay, so CF times L1 squared minus CR times L2 squared. I don't need those parentheses. Oh, well, that's fine. And I'll make this bigger so you can see it. There we go. All right. And now we're going to do this for theta. So again, for now, I'm just going to, pull this out. It's not actually connected to theta dot because we haven't built theta dot yet. Drag that down. Okay, and then I'll copy and paste the gain block here. And this is going to later hook up to theta. So this is going to be KF, the stiffness for the front tires, times the length for the front tires to the center of gravity, minus KR times L2. And we'll make this bigger. All right. And so we can kind of keep track of stuff. Let's actually get some annotation blocks up here. Okay, so for this top one, we have x dot. So I'm just going to copy and paste that annotation. Okay, this is x dot. And then we have x right here. And remember, this one should be theta dot. So I'm going to get a new annotation. So I'm going to do a backslash and then dot. And then inner curly braces theta. I should have a backslash theta. All right. And then we have theta for the last term here. So just backslash theta. All right, there we go. And let's save it in case it crashes on us. That would suck. Okay, so we're almost done. Now all we have to do is get our last four terms, which are related to our input from the road. So remember that was y1 and y2. So for that, we have y1, y2, but also y.1 and y.2. Okay, so for this, let's move these again. Okay, we'll zoom in here. So the first thing we have to do is get the derivative for y1. So we're going to use a derivative block. So we'll type in derivative. And then I'm going to do Command I to flip it. And I'm just going to hook this up to our sign block. So right here, this is still y1 right here. And then we take the derivative. And then after this is going to be y.1. So I'm going to take this out here. Just trying to match it up to how I made my model so it's nice and neat. We'll get an annotation block. And we're going to do a backslash dot y and then underscore 1. Okay, so we have y dot 1. All right, and then for that, if we look at our equation of motion on the slides, we're multiplying y dot 1 by the damping coefficient for the front tires. So we're going to get a gain block, we'll flip it, and we're going to put in our coefficient, our damping coefficient for the front tires, so that's CF. All right, there we go. Everyone following along so far? Hopefully you got the license stuff to work out. Okay, so we have y dot 1, and then we need to have y1. So we're going to put that below. So I'm just going to change this to be y1. And for y1, we have y1 multiplied by our stiffness for the front tires and suspension. So we're going to get a gain block, copy and paste it, and we're going to change this to KF. So the stiffness for the front tires. All right, and then we're just going to hook this up to our sine block, our sine wave for the front tires. All right, let's move this down a bit. And I'll connect it like that. All right, there we go. So if we kind of zoom out here, this right here is our equation of motion for the linear portion, almost. We still need to divide by the mass. So we have all of this. Let's get our addition block. So you can use a summation block or just the add block. So I'm going to use the add block just because that can look a bit neater. And I'm going to flip it. And what we need here is 8 inputs for the sine. So we have 2 right now, so we're going to add in 6 more. And we're going to resize this. All right, there we go. And then let's start connecting this stuff. Actually, I need to disconnect them. We need to have y2 and y.2 as well. Forgot about that. So let's delete those. So we need to have y2 and y.2 because this is a, that's still part of our car still going up and down, and we did the front tires so far, but we also need to have the rear tires as well. So that's y2. So we're going to do basically what we just did for y1, but we're going to do it for y2. So we have our sine wave block down here. We need to get the derivative of that. So let's get that. Let's attach it. And then we're going to multiply that by CR, so the damping for the rear tires. So we'll change this to CR. Hey, Jared, I don't know if you know, but your mic is on.
Sorry about that.
You're good. I just, I want to let you know just in case you didn't know. Okay, so we have the derivative. So this is now going to be y dot 2. So let's change that. We're going to do dot y and then underscore 2. Okay, so we got that. And now we need to have y2. So we're going to copy and paste that. I know it's kind of tedious, but gotta do it. And we're going to change that to KR. So the stiffness for the rear tire. All right, and then we're going to hook that up to our sine block. Okay, so that's y2. All right, there we go. So now we have all of this. Now we can connect them to our addition block here. All All right, I'm gonna, rearrange this stuff so it connects better. Okay, so let's make our block bigger. I won't spend too much time on this, I promise. All right.
Bothers me too if they're not aligned.
Yeah. And of course, if you move some of these blocks and everything shifts, it's really annoying. Almost got it. Almost got it. All right, and then Y2 at the bottom here. All right, there we go. That's good for now. All right, so we almost have our equation of motion. All we have to do is divide by mass. So what I'll do is I'll get this connection. I'll drag it up here, and we're going to get a gain block. And I'll modify this to be 1 divided by m, so that I'll allow us to divide by mass, by the mass of the car, and then I'll connect that there. And let's move this down. Okay, there we go. All right, so that's our equation of motion for the linear portion I'm saying, but that's again our car going up and down. Okay, so this is all of this right here is for x double dot. So there we go. So we got one side. Now we just have to do theta double dot, and then we can actually run this, and then we can look at our output for the bounce of the car, the bounce amplitude, so how much the car is going up and down, and then for the tilt, how much it's tilting like this along the road. All right, so there we go. So we're gonna do the same kind of attack plan, I guess, as we just did for x double dot, but we're gonna do it for theta double dot now. So let me stop sharing my screen really quick. So this is our equation of motion for x double dot, or for theta double dot. So, it looks somewhat similar to what we had for x double dot, but of course our terms are going to be a little bit different. And we're going to be dividing all of this by the moment of inertia about the center of gravity, so that's at j. So the first thing we'll do, we'll start out with the terms x and x dot, then we'll do theta and theta dot again, and then we're going to get those last 4 terms in the bottom that are related to the actual amplitude for the height profile for the road. So y1 and y2. And then of course the derivatives for those. Okay. So first thing, we're going to build, kind of like we did up top here, theta double dot, theta dot, and theta. Okay, so let's get an integration block. I'm just going to copy and paste it over here. I always do that, paste. And then one more. And I'm going to flip these as well. Let me zoom in. Okay, so let's connect them. Okay. So on the left here, this is going to be theta. So let's get an annotation block again. Make this size 18. So once we integrate this twice, we're going to have theta right here on the left. So we'll do backslash theta. Go up. Okay, and then in the middle, we're going to have theta dot. So I'll do backslash dot and then theta. need my backslash for theta. And then over here we have theta double dot. So I'm just going to add another D. Okay, there we go. So we have theta double dot, and theta. Okay, so that's good. Let's get a gain block here. So again, we're going to do the first two terms being x and x dot. So this top one here, we're going to have x dot. Okay, I'll just leave that there. So let's modify this gain block. So if you look at the slides, you can see the term there. But this is going to be CF times L1 minus CR times L2. So we have the damping coefficient for the front tires times the length for the front tires to the center of gravity minus the damping coefficient for the rear tires times the length for the rear tires to the center of gravity. All right, and then let's click apply. Just making sure I typed it in right. Yeah. Okay, and then I'll make this bigger. There we go. So let's copy and paste this. Now let's actually first I'll get an annotation block here. So remember that was x dot. So let's copy and paste that. Okay, that's x dot, and then we're going to get the term for x. Just going to put in an x there, and this block is going to be kf times L1 minus kr times L2. There we go. And now let's do our theta terms. So I'll copy and paste. Let's actually move these up a bit. So I'm going to connect these soon enough. They're basically, they're just going to connect over here. So this will connect to x dot, and then this one will connect to x. But we'll do that towards the end. So now we're going to do theta dot and theta. Let's copy and paste the gain block. We'll do theta dot. So theta dot, if we look at the slides, that's going to be negative CF, the damping coefficient for the front tires, times L1 squared minus CR times L2 squared. Okay, click apply. And that was theta dot. So let's copy and paste theta dot. Keep track of everything. Now we got to do theta. And theta, that's going to be minus kf times L1 squared. And then this will be minus kf times L2 squared. Sorry, kr. So we have minus kf times L1 squared minus kr times L2 squared. Okay, click apply and OK. And that was theta. There we go. So let's move these over to the left here. See, that's the issue. I'm moving some of these and then all of those lines just shifted. Okay, so you should have all of these gain blocks now. So now we have to do the last four terms. So that's y.1, y1, y.2, and y2. Okay, so I'm going to scroll down a bit now. So this part is totally unnecessary. All you really need to do is get this derivative block, from here. But literally just so it looks nicer, I'm going to copy and paste this derivative block and put it on the right side. Okay, because all we're doing is getting that derivative for y1. Technically, we already have it. It's right here. But I'm just going to do this to kind of even out the model. Okay, so that's y1, and then we have y.1. So I'm just gonna copy and paste this. We have y1 over here, or y.1. And then if we look at our slides, y.1, that's going to be multiplied by negative CF times L1. So let's get a gain block. And we're going to change this to negative CF times L1. Apply and OK. Oh yeah, let's save this. We did a lot. And let's make this bigger. There we go. Yeah, you can fix this. I'll leave it for now though. Okay, so there we go, and then we need to have y1. So y1 that's going to connect right here. So looking at the slides, y1 that's multiplied by kf times L1. So let's drag this down. We have kf times L1. Click apply. Sorry, it's negative kf times L1. Didn't see the minus sign. Okay, so negative kf times L1. And let's connect that right there. All right, I'm not going to mess with that. This is y1. Okay, and then we just need to do y2, y.2 and y2. So let's get a gain block again. That's connected nicely now. Oh, but I need to have the derivative. Okay, so let's get the derivative block. We'll flip this. Connect that there, connect that. Okay, so we're going to have y.2. Put that right there. And let's do dot y2. So looking at the slides again, y.2, that's multiplied by CR times L2. So CR times L2, getting the rear tires here. And then we just need to have y2 now. So let's get a gain block. And y2 is going to be multiplied by kr times L2. Kr times L2. All right, and this is y2. All right, let's save that again. All right, so here we go. Here's our model so far. So now we just need to connect a few more things, and then we're going to be done with the modeling. So let's copy and paste our addition block, and then we'll invert it. And let's start connecting some stuff here. Move this down. Okay. So we're just gonna click and drag. Now these should be nice and aligned. Cool. Okay. Gonna move all these down a bit. There we go. All right. Cool. Now, for this, remember we have all of our numerator terms right now right here. And so all we have to do now is divide this by j. I'm going to align these a bit. I don't know, don't like to use the word OCD, but for lack of a better word, I'm OCD about this. Okay, so let's divide this by j. So we're going to take this out. We're going to get a gain block, and we're going to do 1 divided by j. So remember j, that's our moment of inertia about the center of gravity. And then we'll invert that block. Let's connect it. Put that there, and we'll connect that. Okay. We've got this, delete this part here. Okay. All right, there we go. Okay, so we're almost done. Now we just got to connect, a few of our blocks here. So, first thing, we'll do theta dot over here. So this theta dot, that's got to be connected. Yeah, okay. I'll delete this. Okay, so theta dot, let's connect that to theta dot over here. Let's move this actually out a bit more. Yeah. Connect better then. Okay, so theta dot, that's got to connect to this. Move this down. And then we have theta. And I'll connect to theta right there. Okay, so now we connected those. And now we just got to connect these 4 on the right-hand side here. So the first one is x dot. Let's connect that right there. And then we have x. Let's connect that to x. Okay, here's x. Connect that there. All right. So x, connect it there. There we go. And now we just have to do theta dot and theta. So theta dot, we'll connect that just like that. And then theta, just need to drag this over right there. There we go. Let me just take a look, make sure I connected everything correctly. We have x dot, that's going over here. That's connected to x dot right here. X, that's going over to this branch here. That's x right here. Kind of move this over a bit. Okay, and then we have x dot, that's connected here. There's, theta dot. Okay, that's connected. Then we have theta, that's going right here. That's theta. Looks good. Let's check the left-hand side over here. X dot, it's connected to x dot. X, that's connected to x. Theta dot going over here, that's theta dot. And then theta, that's connected to theta. All right, looks good. Okay, so there we go. We have our coupled system, or our coupled equation of motions, basically. So on the left, we have x double dot. That's the car bouncing up and down. And on the right, we have theta double dot. That's the tilt of our car. Okay, so the two things that we're looking at here is x and theta. Oops, didn't mean to do that. Okay, so let's kind of move up here. So let's get 2 scope blocks so we can look at the system response. So I'll zoom in a bit. Or actually, does everyone have this model, or at least most of you? Okay. I'll give you actually like a minute or two to kind of look at this and copy it down, because I know it's going kind of fast. Okay, so what we're going to do though, we're just going to get our scope blocks, and then we're going to run this. We'll take a look at the system response that we have for x and theta, and we'll add in a 2 workspace block for both of those, and we'll add a little to our script to make a plot, and then from that point we're done, and then we'll just have to, or you guys will have to modify the stiffness coefficient and the damping coefficient for these specified constraints for the system. So we need to have our bounce amplitude less than, again, I think it's 2.5 millimeters, and then the tilt, so theta, that has to be less than 10 to the negative 3 radians. Oh, yeah, and that's at steady state. Okay, so I'm going to zoom in now. I'm going to add in my scope blocks up top. So I'll type in scope. I'm going to flip this. So this will be for X, our bounce amplitude. And I'm going to call this bouncy. Okay, and then we'll copy and paste that. We'll flip it. And this one is going to be tilty. Let's move that there. This over here. Okay, so we got those, and now we need our 2 workspace block as well. Okay, so we're going to type in 2 workspace. We'll flip this, and this is going to be, let's rename this and call it bounce. We'll do bouncy again. Okay, and then we gotta flip this one. Okay, I know it's not totally symmetric here. And this is gonna be tilty. Okay, so let's save it. And before we run this, let's change our step size. So we're going to go to the modeling tab and then model settings. And we're going to use a fixed step size of 0.01. So we have a nice smooth curve. Press OK. We'll save this one more time. And on the handout, the duration time wasn't specified, but looking at when I took this lab, I think we left it at 10 seconds, looking at the plots that I had. So we're going to keep our simulation time for 10 seconds. Then we can click run. Now let's pray everything was typed correctly. Let's look at bouncing first. And yep, from what I remember, that looks correct. This zoom bar up top is really annoying. Okay, let's make this bigger. All right, so this is what we currently have. So if you remember back from our control systems experiment, this goes to a marginally stable system. So, we still have this sinusoidal response here. And it's a marginally stable system. Okay, so let's go out of that. The model settings, I just changed the step size to 0.01. So click on that, and then you just need for solver selection, click fixed step, and then under solver details, type in 0.01 for the step size. Okay, and then let's look at the tilt. And same thing, we have a marginally stable system. Okay. So now let's add some code so we can plot this stuff automatically for us and also simulate our Simulink model. So I'm going to go back to my script now. And what I'll do is after I have our defined knowns, I'm going to simulate, or I'll say run simulation. So define knowns, I'll make that a section. Okay, so run simulation, that'll just be, I'm going to assign this to a variable just called sim. So sim equals sim, that's our function. And then we're going to do not Phelan, class suspension model.slx. And then I'm going to make a section for our plots. So for our first one, this is going to be for the bounce amplitude. So that's X. So I'll do bounce amplitude plot. Okay, and then I'll type in a figure and then position. This will be to specify our size. So that's something I like to do. So we're going to type in 1000 by 500. I'm not sure if I ever went over this in this class or it was only my other class, but the first two numbers here are 0, 0. That's where your figure is going to show up once you run the script in reference to this lower left-hand corner. So if I put 0, 0, it should show up in this bottom left-hand corner. I have a window manager on here too, so I think it will actually still show up there, but it might not. Doesn't matter, though. These first two ones don't really matter. These last two numbers, that's the width and then the height. Okay, and then I'll use another command here called visible. And this just makes it more convenient for us. If I want to look at the plot when I run my script, I'll have this set to on. If I don't want it to show up, it can still run the code for the plot, but I can change this to off and then the plot won't show up. Okay, so now we actually want to plot this. So to plot it, it's going to be sim.position. Right now it says out. That's because we ran it first in Simulink. But once we actually simulate it in our script here, this variable here is going to change to sim, because that's what we defined it as here. We said sim is equal to the simulation. Okay, and all we have to do is sim dot, this would actually be bouncy. So sim dot bouncy. And then I'm going to change our Y label to the pitch amplitude. That's what we're looking at, pitch amplitude. And this actually should be meters, I believe. And then we'll do AX equals GCA. That just means get current axis. And then AX dot Y axis. Make sure your capitalization is the same too. Dot exponent equals 0. That's to get rid of our exponent on the axis. So let's try running this. See if it works. Okay, there it is. And yeah, it looks like this is in meters right now. Okay, so get out of here. Let's make this bigger. You know, actually, let's change our line width as well. So on the plot line, I'm going to also add a line width of 2. Okay. And there we go. Here's our plot. Okay, so, you know, of course, I want to see your plots in your memo. So this will be one of the first plots you show for our initial parameters that we have. And then once you start doing this for the damping coefficient and the stiffness coefficient, you're going to show your final plot as well. Okay. Let me look at my slides. I never put it in. I'm just going to make sure, be 100% sure that this is the same. Oh, I don't know if I actually saved the figure. That's gonna kind of suck. Yeah, I didn't. Okay, that's okay. Okay, so from what I remember, this is correct. But yeah. So if we look at this, you just got to look at our maximum value that we have for the amplitude, and later that's got to be less than 0.00025, I think. Yeah. Okay, so that's our amplitude. Now we need to do this for the rotation as well, or the tilt. So I'm going to do tilt, amplitude, plot. And you know, actually what I could do is just go here. I'm going to run my other script. Uh-oh, those numbers are different. Okay, I'll take a look at that in a second. Let's do this plot. So this will be figure. We'll do position. And then I'll do 0, 0, 1,500. And we'll do visible and then on. Okay, and then up here, I'm going to change this to off because I don't want to look at that plot. Then we'll do plot sim.tilty. And we'll have a line width of 2. And then we'll do this Y label. This will be our tilt. And that's in radians, so I'll just do rad. And then we have AX equals GCA. And then we'll do AX. Actually, I don't know if there's any exponents that'll show up here. Let's find out. So I'm going to run our script. Did I type something wrong? Yeah, visible. Visible. Okay, run our script. And here we go. So I'll have to check if these numbers are wrong too. I might have just typed in a number wrong somewhere. I'll have to check that. Because our graphs, they are the same, but the scale is wrong. So I'll see if I can, spot the error right now. But if I can't, then I'll just I'll have an announcement. But our graphs, again, the graphs are correct in shape or response, but the scale is off. Okay, so we have that plot. So let's actually put this to off again. Let's make this one on. Let's run this. And I'm going to move this figure over here. And let's run this one. Let's actually change the line width to. Okay. All right. So yeah, you can see the shape of the response is the same, but our numbers are different. So I gotta check that out. Yeah. Let's go over here again. Let's make sure I typed in all these correct. 3,000, 3,000. Okay, yeah, they all look the same. So maybe I typed in something wrong, like a minus sign or something in our model. So I'll take a look at that. It'll take me a few minutes to look at, and then I'll send out an announcement for you guys for an email. Just to reiterate, the shape of our response is correct, but the scale is off. So I gotta look into that. Yeah. Okay. So are there any questions though before we finish today? And of course, if you didn't get all of the modeling done or the script, I'm gonna upload this as soon as it's done processing on YouTube. But your job will be to look at our response here. You're gonna look at the maximum value that we have. Well, actually, you have to look at steady state, right? So you have to look at steady state. So you're going to adjust the damping coefficient and the stiffness coefficient until you get values that are less than the required constraints of the lab. So that's on the handout, but I'm also going to upload a deliverables handout, sometime in the next few days for what you have to do. But you can get started now where you just need to look at the handout and try to meet those constraints for the bounce amplitude and the tilt. So any questions though? All right. Okay, well that's all I have for you guys today. So we're gonna go over the derivation. If you want, I can give you the derivation if you want, but I'll have to go through that again. So yeah, we just have the modeling. For your final, we're gonna focus on modeling as well. So again, you're most likely gonna be given an equation of motion, and you'll have to build that model on your own inside of Simulink. So, yep, that's it for today. So if you have any questions, you can stick around, but if not, you guys are free to go, and I'll see you guys next week.
Thanks.
Have a good day.
Patrick?